Hello CRO world, and welcome to another installment of Chemical Engineering. In this lecture we will cover fluid movers. Fluid movers generally fall into two categories, namely positive displacement fluid movers and kinetic fluid movers. The positive displacement fluid movers achieve flow through either reciprocating or rotational actions, while kinetic fluid movers make use of centrifugation or peripheral action. The first type of reciprocating fluid movers that we will discuss makes use of a movable diaphragm that pulls and pushes against the fluid inside a chamber, which is referred to as the volute chamber, as shown. At the entrance and exit of the chamber are two valves that open and close depending on the stroke action of the actuator that moves the diaphragm. And in essence, these will act as one-way or check valves. A similar design is used in a piston valve, except that the piston is more rigid, of course. Again, one-way valves are used to ensure flow proceeds in one direction only. These types of valves can be used to achieve high operating pressures and are commonly used with liquid flows. Now, a variation of the piston type design uses a plunger instead, which reduces the cross-sectional area considerably that is being applied to the fluid, and therefore a much higher force can be applied with each stroke of the pump. As such, very high pressures can be achieved in this case. Rotational fluid movers rely on gears that move pockets of fluid from the entrance to the exit as shown. These are mostly used in industries like the oil industry, where you would be working with very viscous fluids, and then such a pump is much better because of the mechanical rigidity. A variation of the gear design is to use screws instead. These types of fluid movers are most useful for things like polymer melts, where you would not only move the polymer melt along, but you could also increase the temperature of the fluid in question by changing the way the vanes or the screws are set. So you can also use this for mixing and extruding applications, where you need to mix dyes into the polymer before you extrude them out into a dye. And so often these screws are used to maintain the melt, to keep the melt hot due to the excessive frictional forces placed onto the polymer. Usually the polymer comes in as beads, and the kneading action heats the beads up. There are sometimes also going to be electric heaters along the sides of the screws. This is not only used for polymer melts, it can also be used in other applications as well, again for fluids that have very high viscosities. Now the following pump is a type of vane fluid mover. So it works on a rotational principle. It uses movable vanes to push the fluid along, almost in the same way that gears would achieve this sort of motion. Just note that these are not the kinetic type centrifugal pumps that you would often see. These vanes also move pockets along. They create kind of batches, so you can just watch the image and imagine to yourself how the flow sections are volumetrically cordoned off and pushed through. The kinetic type fluid movers transfer kinetic energy to the fluid using centrifugation or peristaltic motions. Shown here is a common type of fluid mover, where the impellers suck the fluid through the suction line, which is shown here by the largest arrow, into the center of the axle where the shaft is located. The fluid is then thrown into the volute chamber, before it collects into the delivery line of the fluid mover. Axial type fluid movers are similar, and they rely on the blades that are set around a spiral formation, and they deliver the fluid along the same axis as the shaft. So compare this motion to the previous example where the fluid direction changed perpendicularly as it entered and left the pump. Mixed flow combines the two motions of radial and axial flows, where the blades are used to pull the fluid into the axial position, but where the volute chamber reforms the direction of flow before the fluid is delivered into the delivery line. Sometimes these types of pumps or compressors are used to move along gases. So if you ever look at small air blowers, for example, they usually take on this sort of construct. High-speed fluid movers, such as what is typically used in turbines, make use of the narrow passes between the propellers that both guide and increase the energy transfer to the shaft. The mechanical energy that is transferred to the shaft is sometimes used to drive more fluid through the turbine blades, where there would be propellers in front of the entire setup, pulling a draft into the turbine, such as what is seen in aeroplane turbines. Peripheral type fluid movers guide the fluid along a circuit as shown here, along the periphery of the volute chamber. Other types of periphery fluid movers include peristaltic pumps that actually squeeze a fluid through a tube, kind of like how you would squeeze toothpaste out of a tube, and also how your digestive system, such as your esophagus, your colon, etc., uses the peristaltic type action to push through your food and digested food through the digestive system. Now, for each category of fluid mover that we've discussed, the positive displacement and the kinetic type, there would be a characteristic pump curve that is associated to these. In the case of the kinetic fluid movers, which are in general the pump that you would likely see in industry or even if you go to a hardware store, the characteristic curve tells us how much fluid will be obtained in terms of a flow rate, a mass flow rate, or a volumetric flow rate at certain pressures. Now, usually it's specified in volumetric flow rate because you don't know what mass you are going to be pumping around. You know, it could be water, it could be oil, who knows. The operating pressure is associated with the resulting flow rate according to the system curve from the process in question. The system curve can be shifted to different locations using a control valve or a modification to the process variables. So in other words, the total variable pressure differences. In the case of a positive displacement fluid mover, a flow rate is usually selected based on the frequency of motion of the pulsation. So you can think of this as a drive, kind of like what happens in a car. You put your foot onto the accelerator and you can then accelerate the car, and once you've reached a certain flow rate, you then manage the revolutions per second of the crankshaft, and then the crankshaft will keep the car at the same velocity. So you can imagine that positive displacement pumps are very good at selecting a certain strict velocity or flow rate through the system. Note that a shift in the system pressure can be obtained, but you can also shift the system curve back and forth, and so you can select a flow rate and you can also specify a higher or lower operating pressure based on the constructions such as a control valve, which would block the movement of the fluid and increase the pressure until the pressure drop across the control valve becomes stable. So what do you think would happen if a pipeline suddenly experiences a block? The blockage could be due to the fluid itself, or it could be due to a faulty valve that closes fully, blocking the flow. How would each category of fluid mover react if there was a blockage? What would happen in the kinetic fluid mover example, and what would happen with a positive displacement pump? And what consequences could there be for the process and also process safety? So give some thoughts. I think we're going to discuss this at the end of the lecture. Now let's consider a quick analysis of the following pump curve. Notice that the pump curve combines the pressure head for the pump with its net positive suction head, as well as the power usage. And also sometimes the energy efficiency of the pump is also given, and the pump curve is also shown here in a range of values, because it can change depending on variations in the actual mechanical construction of the pump, and also how the fluid interacts with the pump in question. So for this diagram, the energy efficiency are drawn as lines. So these lines representing energy efficiency appear in the yellow shaded region of the top part of the graph. Alright, at the top portion, the system curve is also plotted here. I've plotted it myself, and the resulting operating point is shown by the red arrowhead. At this operating point, we have a pump efficiency obtained of 84%, and we will likely obtain a flow rate of around 1000 US gallon per minute. Now note that the flow rate is common as an x-axis for all the graphs, and so we can go on to determine each set of parameters for this pump. So at the specified operating point, for example, the pump will likely deliver 100 foot of pressure. So remember, this is pressure head. It can be easily converted to kPa if you know the density and gravitational constant, of course, for the fluid. The net positive suction head can also be read off thus, and remember, this is the required net positive suction head for this pump. Okay, so this is what is required, and we go to the process that we've designed, and then we calculate what is available, and we try to match that with the required net positive suction head. And then lastly, we can also read off the predicted power usage. This is not the actual power usage that the pump would use. You would actually need to manually measure this, and you'd probably ask the electricians or the machine mechanics to do the measurement for you. Now, how do you go about selecting the right fluid mover? It can be quite simple if you know what you're doing. Firstly, the type of operation should be considered, as well as the construction material that is required for the process. What is the impeller constructed out of? Is it brass? Is it plastic? Is it stainless steel? Is it nickel? Is it Hastelloy, etc.? And also the mechanical design. How does the pump work? How does it operate? Are you going to have any electrical sparks that you need to protect against because you may be pumping a flammable liquid, for example? Now, once all of this is known, all these details are known, the characteristics for the fluid mover can be chosen to match the particular characteristics of the system that will be using it, of course. Now, as a general guideline, your go-to pumps are going to be centrifugal pumps. These are the most suitable for most of your applications. They get very good flow rates out, and they deliver acceptable pressures for any type of process. It is for particular processes that you will start looking at other types of pumps. So where high pressures are required, so if you want high operating pressures, 300 bar up, positive displacement pumps should be used. Now here I show that anywhere from 30 bar upwards, you would typically want to use a positive displacement type pump. Now if high viscosity fluids are to be pumped, then of course a gear or screw type fluid mover should be selected instead. Diaphragm pumps are most suited when you have to work in a corrosive environment where the diaphragm protects the rest of the pump construction from seeing the fluid in question, while a positive displacement pump offers a better flow rate control than the other types. A diaphragm pump can also be used when you have perhaps large mixtures of fluids, or if you want to also pump air, for example. These little fish pumps even work on the diaphragm principle, where they create a good seal so you get some good movement out volumetrically, but they can also be used for liquids. The following diagram is a typical diagram that shows the operating regions for various pumps. And you can pause here for now and then just study this in your own time to orientate yourself where, with regards to where each type of fluid mover would sit. So for example, look at the actual flow, look at the types of flows that are achieved versus a reciprocating type pump. Look at the range where centrifugal pumps usually tend to operate. Compare this with a marginal centrifugal operation instead. Okay, so go through this and see that you more or less have a feel for different types of pumps. Usually when you specify a type of pump to be used, then you would be given a lot of options by the manufacturer from which to select. So let's say we've chosen centrifugal pumps, so the following would be the various types of centrifugal pumps that are on offer by the supplier, and those pumps that fall or match within the desired flow rates and pressures as well, the pressures of operation. These pumps would then be selected. So let's say I want 200 US gallons per minute and I want a flow rate of between 200 and 400. Okay, and then I need to deliver a pressure of 200 foot. Then I would select either pump 6, 7 or 8, and perhaps I'll go for 7. Maybe it's just cheaper than pump 8. Now the next thing to check is the maximum pressure exerted at the delivery flange of the pump. This is where the pipeline connects directly to the pump in question. So the pump is a unit. It will have a flange on either side where the suction line and the delivery line goes, and then you would just put another flange, pipe flange onto that. You'll bolt it closed and Bob's your uncle. Now for positive displacement pumps, the top equation is generally going to be used where the maximum linear velocity is applied. This is the expected linear velocity that you would typically achieve in the process. For centrifugal pumps, the bottom equation is going to be used instead. It should be noted that if the delivery line following a positive displacement pump is closed at all, I asked this question earlier on in the lecture, what would happen? Well, what would happen is the pressure would simply build up more and more until mechanical failure is reached, because the volume of fluid that you are now pushing into the pipe has nowhere else to go but remain inside the pipe, and on top of that you add more and more and more volume, and as you increase the volume you increase the density of the fluid, and eventually this would likely result in a burst pipe wall, which is obviously going to be detrimental to the process, and you can harm your fellow colleagues if this is done. If you have learned before about pump efficiency, which you probably have when you were doing COP, this concept centers around how much work is delivered to the fluid versus how much energy is going to be required by the pump. Okay, so the energy that is delivered to the fluid is referred to as the hydraulic work that is achieved, whereas the real work that is required is the energy that is needed by the pump to operate and deliver the hydraulic work to the fluid. So therefore the efficiency is the ratio of hydraulic work and real work. Okay, so let's say the hydraulic work was 80 and the real work was 100 cabbages or watermelons, then we get an efficiency of 80% or 0.8. Okay, the total work that is delivered to the pump is easy to determine from the electric readings that can be obtained during the pump's operation. You just measure how much electricity you're putting into the pump, or how much electricity the pump is utilizing. The hydraulic energy is computed using the following equation, which uses the mass flow rate of the system. Now, since W has units of kilogram per hour, we divide by 3,600 seconds per hour to complete the calculation shown. This calculation is useful as the pump characteristics specified by the manufacturer may not always be realized in your system. It all depends on the fluid in question and the operating conditions, of course. And so a quick check of the efficiency is therefore completed manually using this equation. Now lastly, the effects of combining pumps in series and parallel are to be known by you. So you should know this. When placing two pumps in series, the flow rate delivered when placing two pumps in parallel, the flow rate that is delivered will be the sum of the individual flow rates obtained by the individual pumps, whereas the pumps that are placed in series would combine the delivery pressures of each of the pumps, and these will maintain the same flow rate. So you can imagine a flow rate coming in to the first pump at 100 meters per second, and then it leaves at 100 meters per second, but it leaves at a higher pressure. So the suction line of the second pump sees this higher pressure and it adds to this pressure a further pressure. And so this is why pumps in series add to the pressure but will keep the flow rate constant for this setup. Okay, and with that we end off this lecture.